Good morning everyone. My name is Vin. I'm a PhD student from Texas Tech University, USA. I'm very honored to be giving my presentation today. As you all know, water is the basic element that human relies on for all living and manufacturing activities. As rainfalls are not equally distributed in the world, surface water does not meet the demand to sustain in many areas. In this case, it is necessary to turn to groundwater found in aquifers to support daily activities. Wells drilled in these areas must reach to a certain point to pump up water, and this point is known as the saturated thickness, which is the distance between the water table and base of the aquifer. The Ogallala Aquifer in United States is a groundwater storage reservoir that stretches 174,000 square miles underneath path of 8 states from South Dakota to the Texas in United States. The Ogallala Aquifer of Texas provides 96% of underground water for irrigation and 36% for municipal demands, and thus plays a critical role to the economical development of this region. According to the Kansas Geological Survey, groundwater levels in the aquifer have dropped an average of 14 feet since 1996, about a foot each year, especially in the Texas region. For this point of view, there is a need to have good water management strategy for a sustainable use of the aquifer system. One necessary requirement is to continuously monitor groundwater levels. A number of studies have been conducted to address the challenges of the Ogallala aquifer systems and provide some projections. Typically, these studies can be classified into two main categories. The first one is to use statistical method combined with economy impacts. For example, the study of economic growth, land use to give prediction of saturated thickness by 2050, as studied in Dutton. But these factors are not stable due to the changing of economical growth or expansion of non-agriculture areas. The second one is applying multiple machine learning models to give the prediction. These models are compared to each others and choose the one that give the best result. However, it requires a deep knowledge of expertise in machine learning, and choosing a good parameter to feed into these models is an art. For this point of view, it poses two questions that we're seeking to address. The first question is, how can we apply machine learning to tackle our problem as a non-expert in machine learning with least effort? The second question is, as a non-expert, how and to what extent can we understand our model? These two questions are the main talk of my presentation today. We approach the problem by applying LSTM model to give the prediction of the saturated thickness based on Keras API, and using tensor board visualization as a tool to understand the model. Why do we use LSTM? As mentioned in the previous slides, there are multiple methods to solve the time series problems, and in the study of Seema Siami, they showed that LSTM give better result compared to other models. And why Keras writing bunch of codes is a tedious task, especially for non-expert in machine learning. And Keras API allows you to go from idea to result with least effort. Coming back to our problem, we have a historical data with different variables of features and one target value, which is the saturated thickness. What we want is to predict the values of the saturated thickness given the historical data. Our approach is to convert our problem into a regression problem by shifting data back to 1 or more months. The saturated thickness of the current month will be used as a variable to predict the saturated thickness in the next month. Configuring the model to train the model is simple with only 4 lines of codes when using Keras API. You define the model, train it, and hit run, and you got the result. But the next question is, what's happening inside that model right now? I have no idea how it works. That's why we need tensor board visualization to visualize, debug our model configurations, TensorBoard includes many components such as scalars, images, graph. We mostly focus on TensorGraph, scalars and debugging, because I think that's enough to understand our problem. First, you create a log folder to store the events generated by the model. Second, you activate the TensorBoard, pointing the working directory to the log folder. And finally, you open a browser with the following address to run TensorBoard. The first thing we see is the tensor graph, which is shown on the screen. TensorGraph consists of nodes and links, where nodes are operations, and links are data information flowing between nodes. The second tab on the screen is the scalars, which allows you to see changes in the error while training the model by putting another parameter while activating TensorBoard. TensorBoard allows you go into debug mode, in which you can see how your data is changed in each step. Go back to the main part, which is the tensor graph. The question is, how can we interpret this graph? I find it useful to take you back to the basic idea of machine learning first before talking about this. Suppose we have a simple linear problem which is to predict the second value based on the data in the previous row. Solving this problem is simple, isn't it? Just only finding the weight of the variable and plug it into second row. A problem gets a little bit complex by having more data. Finding only weight is not enough. We need another factor. That is bias. When the problem is small, we can solve it manually. What happens when we have hundreds or thousands of data? This is when machine learning shines. We teach computer algorithms, and they will do the rest for us. Let's take a look at a simple perceptron in machine learning. It takes input data, performs a summation, passes the data to activation function and give the result. Depending on the types of problem, you may have different activation functions. To simplify our demonstration, we put bias term as a weight with unit input. Let's demonstrate with an example. We have a table with 4 rows of data, 2 inputs, and 1 output. Our purpose is to find weights and bias so that, for any given input, it produces the same result with the given output. The algorithm provides the necessary step to solve this problem. First, we initialize a weight vector. Second, select a random sample from training input. For easy to follow, I make it sequential. Third, compute the output y by taking the dot product of the training input with the weight vector. The result is -2, which will be passed through the activation function, providing the output of 0. Because the predicted value equals to the true value, which is our output value, we do nothing. Move to step 6. Repeat this process again. Row 2 gives the same result, so we move to the next row. At this time, an error occurs. We update the weight vectors based on the formula given in step 5. After updating the weight vectors, we move to row 4 with new updated weights. After running through all samples in our dataset, we achieve the final weights, which is -2.4, 2.6 and 1. We don't know if these weights give the correct result. Then we run it again. First row, it's good. Second row, it's good too. Third row, error occurs again. The weight vector needs to be updated. Last row, the prediction is correct. So we have the same question with the previous iteration. We run it again. At this time you can see that there is no error. We get our final weights -2.8, 2.2 and 1. Our question for this learning algorithm is, how can we sketch out, visualize our algorithm? How do we know if any one part of the algorithm is not wired up or programmed correctly? To answer these questions, we use TensorGraph to visualize our model, reading the graph from bottom up. First, the weight vector is initialized by an init function. Second step, input data is read. Third, the predicted value is calculated. by passing the result of the dot product of input data and weight vector to the activation function. The Y node on the screen is the constant value, which is 0. Step 4 is performed by comparing the predicted value with the true value. The result of this step is the input to the step 5. As you can see, in step 5, change in weight is calculated by multiplying the input data with learning rate and the error. Next, we update the weight vector by summing up the existing weight vector with the change in weight vector. Step 6 is shown by the orange line, which is the control dependency line, meaning that the weight vector must be updated before going to the next iteration. As you can see, this tensor graph describes exactly our simple perceptron algorithm. Based on this graph, we can visualize our model to check if there is any missing part, or parts that did not connect properly. For more complex operation, showing all operations on the screen will be messed up. We often group operations in the same function together, then drill into them on demand. Showing operations can be done by double-clicking onto the nodes or onto the plus sign at the top right corner of the node.